This video was sponsored by Let's Get Rusty. Everybody knows that Electron apps, like Discord, are essentially web applications. This kind of software uses a multi-process architecture, which means that behind the scenes, when you open one of these apps, multiple processes start running in the background and communicating with each other. The reason we don't really notice this is that we usually only interact with the process responsible for displaying the graphical user interface. One recurring question I get is why we don't have to manually start each of those processes. I mean, if Discord is basically a web page rendered inside a fancy web view, why don't we have to manually start the local server that serves the web files, then open a browser, and type a local URL just to see the app? Today, we're going to explore how processes can create other processes, and how this seemingly simple operation works very differently depending on the operating system. Hi friends, my name is George, and this is CodeCrafters. Many applications are designed so that, once launched by a user, they can programmatically spawn new processes at any point during their execution, without any further user intervention. Let's begin by asking ourselves one question. What would a process, let's call it P1, need to do in order to create a new process, P2? Well, for starters, P1 would need to load P2's executable code into memory so the CPU can begin executing it. But right here, without even going any further, we already run into a major problem. On modern operating systems, this is not something a regular user process is allowed to do. Each user process is restricted to a specific region of memory assigned by the operating system, what we call its address space. Any memory outside of that region is completely inaccessible to the process, even if that memory isn't currently being used by any other process. So while P1 can read P2's executable file from disk into its own memory, it has no way to place that code into a different memory region outside of its address space. In other words, P1 has no way to create a brand new process entirely on its own. And this is just one of several reasons why process creation cannot be handled entirely in user space. When this functionality is needed, it must be delegated to the operating system through system calls. For those unfamiliar, system calls are simply an API provided by the operating system that allows user processes to request operations they are not allowed to perform on their own. These operations can involve access to hardware, like reading a file from disk or writing characters to the screen, or they can be services provided by the OS, such as retrieving system information, creating communication channels between processes, or exactly what we care about here, process management. This API is typically exposed as a set of C or C++ functions that programmers can call when they need one of these services. One way I like to think about system calls is this. They're functions that are invoked from user space but executed in kernel space. The operating system performs the requested task, and once it's done, execution returns back to user mode. The catch is that every operating system has its own design philosophy, which often leads to incompatible APIs. Both Windows and Unix-like systems provide system calls specifically for creating new processes. At first glance, it might seem like incompatibility isn't much of an issue here. It looks like all we have to do is call the right function for whatever platform our program is running on. But if we compare the definitions of these system calls, something immediately stands out. I know what most of you are thinking. Windows doing Windows things. And while I agree that the Windows version looks unnecessarily complicated, the Unix/Linux version is actually weirder. To understand the Windows approach, I'm going to oversimplify it into a conceptual function called createProcess, which takes just two arguments. Image is simply the full path to the executable file of the program we want to run, so the operating system can locate it on disk and load it into memory. Command line is exactly what it sounds like, a string containing the full command line used to invoke the program. This includes any arguments passed to the new process, and it's how the process knows whether it was launched with flags or options. In very simple terms, this system call tells the operating system, create a new process using this executable. The OS will locate the file on disk, find a free region of memory for the new process, load the executable code into that memory, and perform all the steps required to insert the process into the scheduler. It also passes the command line string so the new process can parse its arguments before running any user code. Not too hard, right? Well, the Unix counterpart is a bit more interesting. On Unix-like systems, a user process can invoke the fork system call to create a new process. The interesting part is that fork takes no arguments, which means there's no way to specify which executable should be run. Instead, when the operating system receives a fork request, it clones the calling process. The entire address space of the parent process is duplicated: the text section, data section, stack, and heap. And it's not just memory. Almost the entire process context is cloned as well, with only a few small management-related exceptions. As we've discussed in previous videos, that context also includes the CPU state of the process. Let me show you an example. After a quick message from Let's Get Rusty. Have you noticed that more and more companies are including Rust in the development of their critical systems? That's not hype, that's happening. If you are thinking on leveling up your Rust skills, whether for personal growth or to land a job working on real systems, Let's Get Rusty is the go-to place for Rust training. Created by a fellow YouTuber and one of the most beloved names in the Rust online community, Let's Get Rusty has helped thousands of developers, myself included by the way, master the language and break into systems programming. They're running a new cohort very soon, and since spots are limited, now's a great time to check it out. Visit letsgetrusty.com/startwithgeorge, or just click the link in the pinned comment below. Big thanks to Let's Get Rusty for supporting the channel. And now, back to the video. Here, I have a program that declares a variable I and then enters a loop with 5 iterations. On each iteration, it increments the variable, prints its value, and then sleeps for 1 second. After that first loop, the program calls fork, and then enters a second loop that does almost the same thing. It keeps incrementing I and printing its value every second. If I run this program, you'll see that before the call to fork, everything behaves normally. But as soon as fork is called, the output is duplicated. This happens because when the child process is created with fork, it inherits the CPU state of the parent. That includes the program counter at the exact moment fork was called. As a result, both the parent and the child continue executing from the same instruction, right after the fork call. So the child does not start from the beginning of the program. Now, something important to be aware of is that fork can be dangerous if it's not used carefully, especially inside loops. Let's go ahead and call fork multiple times and see what happens. In this example, I'm calling fork 3 consecutive times, but the message is printed 8 times. The original process executes the first part and then calls fork, creating one child process. Now both the parent and the child execute the next line, which is another call to fork. When those 4 processes reach the next fork, each one duplicates itself again, leaving us with 8 processes in total. That's why the message appears 8 times. There are 8 processes printing a message once every second. Now, I'm pretty sure that about half the people watching this video already know where all of this is going. But for those who don't, you might be wondering, what's the point of cloning processes if they're just going to keep doing the same thing? Isn't there a better way to load an executable file and run it, like Windows does? Well, it turns out there is, but once again, it's weird. Enter the exec VE system call. As you can see, unlike fork, this Unix/Linux system call does take parameters. Once again, I don't want to overcomplicate things, so we're going to use a simpler variant called exec v. The arguments passed to this system call are exactly what they sound like. Path is the path to the executable file we want to run. argv is an array of pointers to C strings that defines the argument vector passed to the new program as its command line arguments. So, for example, this command in the terminal would look like this if executed programmatically using system calls. This might look very similar to the Windows approach. It might seem like the only difference is how arguments are passed, in Windows as a single command line string, and in Unix/Linux as an already parsed argument array. But that difference is actually the least important one. As I mentioned before, on Unix-like systems, the only way to create new processes is by cloning existing processes. So, what does exec v actually do? It doesn't create a new process at all. Instead, exec v replaces the program currently running inside the calling process. When a user process calls exec v, the operating system locates the specified executable file on disk. But instead of creating a new process, it resets the calling process entirely. The stack is reset, the heap is cleared, and the contents of the text and data sections are discarded. The CPU state is reset as well. Then the OS loads the new executable into memory. Since the program counter is reset, it now points to the first instruction of the new program, which starts executing from the beginning. The argument list is also loaded into a specific memory segment so the new program can access it. In other words, exec v is used to transform a process, formally defined as a program in execution, into a different program, but it doesn't create a new process. Yes, it's weird, but that's how it works. Let me show you an example. This program starts by printing a message. Then it calls exec v, passing the path to the Google Chrome executable along with a couple of arguments. After that, it prints another message. If I compile and run this program, you'll see the first message printed, and then the program turns into Google Chrome. The last message, however, is never printed, which makes sense. Once exec v succeeds, the current program is replaced entirely, so execution never reaches any code that follows the call. Very interesting, isn't it? But after all of this, we still haven't answered the main question. I mean, fork clones a process, exec v transforms a process, but none of these is really what we need. The solution is actually kind of hilarious. What if a process first calls fork, letting the operating system clone it, and then only the cloned process calls exec v, replacing itself with the desired program while the original process continues running? Believe it or not, this is how process creation works on Unix and Linux. Almost all user processes are created using this pattern. The only remaining problem is this: how do we make sure that only the child process calls exec v? Because if we call fork and then immediately call exec v, both the parent and the child would execute it, and both would transform. We need some way to distinguish them in the source code, so only the child calls exec v, so we need to figure out how to do that. The answer is the process ID. Every process running on a system has a unique ID. When fork is called, almost everything is duplicated, but the process ID cannot be, because it must remain unique. Technically speaking, each process could tell whether it's the parent or the child by looking at its own ID. Unix and Linux system provides another system call for this: get PID. This function takes no arguments and simply returns the ID of the calling process. So here's the trick. Before calling fork, the process calls get PID and stores the result in a variable. Then it calls fork. Since memory is duplicated, both the parent and the child now have the original parent process ID stored. After that, both processes call get PID again. If that ID is the same as the one obtained before, that process can identify itself as the parent. If it's different, that process can identify itself as the child. That logic looks like this. After fork, both processes continue executing from the same point and run the same next line of code. But because they are separate processes with different IDs, get PID returns different values. This causes the conditional check to succeed in one process and fail in the other, splitting their execution paths. That's why the function is called fork. It's not meant to just duplicate a process and keep everything identical. It's meant to fork the execution flow. In fact, if we look more closely at the definition of fork, we'll see that it actually returns a value. Just like get PID, fork also returns a process ID. The system call is implemented in such a way that, in the child process, it always returns 0, and in the parent process, it returns the ID of the child just created. This is useful because it means we don't need to make extra system calls to figure out which process is the parent and which one is the child. We can't know at compile time which process ID the operating system will assign to the child, but we do know one important rule. In the child process, fork always returns 0. That single guarantee is enough to decide which code should run in the child and which code should run in the parent. So when we run this code, the call to fork creates the clone. After that, both the parent and the child receive and store the return value of fork, which is different in each process, and then compare it. If the value is non-zero, the code is running in the parent process. If the value is 0, the code is running in the child process. And this is how we can use the fork function, not just to clone a process, but to tell each process what it should do. So if we want to create a function that spawns a new process without disrupting the calling process, it could look something like this. Of course, system calls can fail, so it's always a good idea to handle error cases properly. Finally, some of you may already be familiar with a function called POSIX spawn. This function is provided by POSIX compliant systems to spawn a new process. However, it's important to note that is not a system call. Conceptually, it looks something like this. If you look at its implementation, you'll find that internally it does exactly what we've been doing. It creates a child process and then has the child call exec ve. And with that, we have a clear explanation of how processes are created on both Windows and Linux. In short, on Windows, a process can use a system call to ask the operating system to create a new process, and Windows does exactly that. On Linux and Unix-like systems, a process must first ask the operating system to clone itself. Then, the cloned process asks the operating system to replace its program. Notice that on Unix-like systems, all user processes are created by other user processes. That means the parent process was created by another process. This naturally forms a process tree that raises an interesting question. If all user processes are created by other user processes, then eventually there must be a single process that started everything, right? If you're running Linux, you can actually see this by running this command. The output is a text representation of the process tree, and as you can see, there is indeed a single process at the root. Where did that process come from? If all user processes are created by other user processes, how does the very first one exist? It turns out that this single process is actually the key to understanding where we draw the line between the kernel and the operating system, which is, by the way, one of the most common questions I get. That, however, is a topic for another video. The reason I'm showing you this is that it's the perfect proof that a single process can spawn an entire subsystem of processes to achieve something much greater. So, going back to the very first question of this video, when you launch an app like Discord, what you're really doing is starting an executable that becomes a process whose primary purpose is to spawn multiple cooperating processes that make the application work the way we know it. I'm going to go ahead and wrap it up for now. If you enjoyed this video or learned something new, please hit the like button. And if you want to learn more, subscribing is completely free. See you in the next one.